Welcome and thank you for joining us today. The American Society of Transplantation is proud to present today's webinar on Applications of AI to Liver Transplantation. This webinar is part of a series of educational offerings on the applications of AI to transplant, developed by AST's Transplant Administration and Quality Management COP and Thoracic and Critical Care COP. Today's session is sponsored by AST's Liver and Intestinal Community of Practice. In a moment, I will turn the session over to our moderator, Dr. Mamatha Bhat from Toronto General Hospital Research Institute, United Health Network. However, before we begin the main presentation, we do have a few housekeeping notes to help you engage with today's session. There is currently a viewership polling question displayed for the audience. Please take a moment to answer this question while we finish the remaining announcements. This webinar is being recorded and the archive will be available on the AST YouTube channel in 2 to 3 business days. Please note that your lines have all been muted so that only the presenters can be heard for the archived recording. If you have a question for our panelists during the webinar, we do encourage you to participate using the Q&A button in the Zoom webinar panel. Questions submitted via the chat window may be missed during the presentation. Finally, when you log off at the conclusion of today's webinar, you will see a link to a short evaluation survey to complete. Please fill out the survey to help us keep our content current and engaging. I will now turn the session over to our moderator, Dr. Bhat, to begin our presentation.
Good afternoon, everyone. It's a real pleasure for me to moderate this first session on AI and liver transplantation. I think it's really exciting for me to moderate this session where we have our wonderful speaker, Dr. Ali Strauss, joining us today. So artificial intelligence tools have been increasingly applied to questions in transplant medicine in recent years. There's been tremendous developments in AI in healthcare, including not only development, but also deployment of tools. In transplant specifically, I think there are many challenges throughout transplant medicine that could be better addressed given the complexity of the decisions we make, the complexity of the patients we care for. There are various factors that affect liver transplant pathology and outcomes. There are complex nonlinear relationships and patterns in terms of the data that is collected in transplant medicine, lots of different types of data being generated. And the reality is the human brain can only process 4 variables at a time. So there's really a lot of potential for AI application in transplant medicine and specifically liver transplant medicine. In terms of applications of AI in transplant medicine, these include the categories of waitlist prioritization, donor-recipient matching, and short and long-term outcome prediction. And so in the webinar today, we have the pleasure of having Dr. Ali Strauss present on the applications of AI tools in liver transplantation. Dr. Strauss is a transplant hepatologist and assistant professor of medicine at Johns Hopkins University School of Medicine. She is director of the Liver Disease Precision Analytics program at Johns Hopkins University School of Medicine. Dr. Strauss completed medical school at the University of South Florida. She continued at USF for internal medicine residency, where she also served as chief resident. She then went on to Johns Hopkins University for fellowship training in gastroenterology, followed by a fellowship in transplant hepatology. Her research training began when she completed a master's degree in industrial systems engineering at USF. Later, at the Johns Hopkins University Bloomberg School of Public Health, she earned her PhD in clinical investigation. Currently, Dr. Strauss's focus is on the use of systems engineering and data science to improve health equity for patients with liver disease. She is a faculty member in the Johns Hopkins University Malone Center for Engineering and Healthcare and the Center for Data Science in Emergency Medicine. So it's my great pleasure to welcome Dr. Strauss to start her talk for today. So she will give her talk and we will follow this up with a Q&A session. So I welcome your questions online, and we hope to have an exciting discussion following Dr. Strauss's talk. Thank you.
Thank you, Dr. Bhat, and good afternoon, everyone. I'd like to start by just thanking the AST for inviting me to speak with you all today about this very important topic. It's also an evolving topic. These are my conflicts of interest. I have none, no financial relationships to disclose, and these are Dr. Bhat's disclosures. For a fantastic primer on artificial intelligence, I would encourage you to check out the first video of this webinar series by Dr. Dori Segev. So I will aim to build off of that and provide examples of applications that are specific to liver transplantation. And my goal for you all with this presentation is for you to have a general understanding of the landscape and opportunities for AI in liver transplant. And I also hope that you'll be empowered to ask questions that encourage cautious but informed AI development. So let's start with this very simplistic version of the liver transplant process. We all know it's a lot more complicated than this, but what we'll be doing is walking through examples that I've chosen from the literature in order to provide you with a diversity of AI principles and methods, while also covering each of the steps along the way. So I'll start by delving into this time when a patient's referred and undergoing evaluation for transplant. This is where our team's been focusing, and my research interest is in this concept of algorithmic fairness, because AI tools are inevitably popping up all across the whole transplant process. So I wanted to understand how to prevent them from worsening disparities that we know exist, and maybe even how we can leverage them to actually be proactive and address health equity. I decided to dive into this evaluation process because that seemed like where AI applications would really struggle the most because of with the concept of algorithmic fairness, because of all of the things that we do during that time of the whole process. So when we were beginning our journey to understand the complexities of the racial and ethnic disparities that arise during liver transplant evaluation and how AI might be helpful or harmful, I wanted to leverage some key human factors engineering concepts, specifically one called the Systems Engineering Initiative for Patient Safety, or SEEPS. And SEEPS is commonly used for assessing socio-technical systems, which is where people and technology come together, and looking at how and evaluating interventions or problems within healthcare. So the key components that guided our research analysis used this model that focuses on work systems, processes, and outcomes, and then this adaptation feedback loop. So the work system is made of people and tools and technology to perform tasks, and then the work system engages in physical, cognitive, and social behavioral processes. And these processes involve individuals and their collaboration together. So that can be professionals, the providers, and patients. And then the results of the work system and the processes that they're undergoing result in outcomes. And those can be represented across several dimensions of measurement, whether at the patient level or an organizational level. And then those have those feedback loops for adaptation that may impact at the back to the work system and future engagements with the processes that they go into. So importantly, all of this is also happening within an external environment that is also impacting how all of these things are working together. We performed ethnographic observations and semi-structured interviews across 2 large transplant centers. And we developed a semi-structured interview guide that was informed by these human factors engineering principles and the literature, including the SEEPS model. And we adapted the SEEPS model to create a conceptual framework that was specific to mechanisms of racial and ethnic disparities in liver transplant evaluation, with the goal being that we need to really understand what was happening there before we go throwing technology at anything. So starting with the external environment, the transplant team members that we interviewed perceived decisions about listing were influenced by external factors, such as structural racism throughout time, whether it's historical or present, national guidelines, state and federal policies, and societal cultures about cirrhosis itself and those pressures that are on the patients. And next we found that the work system was composed of tasks of the patients, their support systems, and the providers. And these are essentially the who, what, and where of the process. The people doing tasks and using tools and technology. And for our example, all within the transplant centers and the local health system. And then they discussed that they interact throughout the process from when the referral is received, workup committee, and patient being informed of the outcome. And then these result in outcomes that are related to and contribute to racial and ethnic disparities. And these can be things like what the listing decision is, people having incomplete evaluations, delay in evaluation. And then some participants described this feeling uncomfortable with decisions that could lead to listing disparities throughout this process. So we called that the decision comfort. And then last is this adaptation concept, and the participants we interviewed talked about M&M conferences potentially being a form of adaptation that has a feedback to how future things play out, and then the potentially provider team member feedback is a way that people sort of can slowly change their behaviors for the better or the worse. So with this framework, we were able to delve in and develop themes. And I'm only going to focus on one of the specific themes because it's relevant to specifically today's talk, but it's regarding the intersection of the tasks that everyone's doing, particularly the providers, when it comes to the committee meeting. So that piece of the process, what's happening. And two of the themes that we found at that intersection were they identified that there's subjectivity and inconsistency in decision-making. And this was a quote that came from our research that was from a transplant team member that said, if you're conveying information that's very subjective about a patient, you have to be careful about the way you say it to not kind of skew people's thinking about the patient. And there was a second theme also at this intersection about implicit biases and personally mediated racisms in decision-making at these committee meetings. So I'm sure for many of you, most of you probably on the call, a lot of this stuff probably rings true to what you see as well. So we wanted to fully understand the process to really know where transplant teams saw opportunities for AI, as well as what perceptions were for using AI at all for evaluation. And so we performed further analysis with semi-structured interviews with those two transplant center teams. And here you can see a process map created through their descriptions where it starts on the left at referral being received. And then this represents a patient moving all the way through to the committee decision where they're either declined, accepted, or deferred. And then they defined essentially breaking this process into two parts, the workup and the committee meeting. The various shapes represent where decisions are made, like the diamonds, and then where communication is happening, the wavy lines. And the colors highlight how many different types of providers are involved across this very complex process. You'll notice that there's little hexagons, and those represent where they identified potential for AI support. It's very important to understand the processes before we go figuring that this is exactly where an intervention is needed most. So from discussing with them, the participants, we were able to identify 6 major themes. And this is a conceptual model of how they described AI CDS tools and considerations for the equitable use in transplant evaluation. So the 2 broad breaking points were CDS specifics, so things specifically having to do with the clinical decision support tool, and then things that had to do with the decision making that AI might help with. And then those feed into these concepts of explainability and transparency and fairness that are standards for things that we need to be measuring and thinking about with AI implementation. And then those sort of the way that they pictured it is they feed into this concept of them feeling like there's trustworthiness with that AI tool. So I'm going to give you a few more quotes that sort of are the representative quotes for each of those 6 themes. So one of those themes was the opinion that the AI CDS could mitigate emotions and biases by being objective. So we're human. This is a quote from one of our advanced practice providers. We're human, so I think that we have emotion, and we sometimes can allow emotions to play into our clinical decision making. And that can be a good thing or it can be a bad thing. And sometimes I think taking that emotion or that personal experience out of it would occasionally potentially be a good thing. A tool wouldn't care if you're rich or you're poor, and a tool wouldn't care if you're Black or if you're white. So another one of the topics that came up was AI-CDS as a new member of the transplant team. So when compared to artificial-based decision-making, participants described this human intelligence-based decision-making as sort of a double-edged sword, particularly related to equity. On the one hand, it was described as human intelligence-based decisions are frequently flawed. Even if they're unintentional, they can be subjective and emotions are involved. Conversely, humans can incorporate hard to quantify and intangible information into their decision-making that the participants felt that the AI clinical decision support tools wouldn't be able to capture those nuances. And there's some just very special and unique circumstances. They also would have a hard time understanding how the AI-CDS could incorporate patient resilience and patient motivation. So these were some things where it's the way that they described it was the human aspect is sort of double-edged. And then for this reason, the participants wanted AI to function more as another voice on the team or a starting point, but not as the final decision that replaces them. They didn't see how that would be possible. So this quote from one of our social workers said, "I think that those tools are great for baseline, that I can put all this into some type of calculation. You have a baseline to be able to build upon, and then that's it. I don't think it should be concrete, like you have this and then it's this." And then another theme was that they wanted AI-CDS to help with identification of patient resource needs. So if there was a tool developed that could help us make our decisions as far as what patients we need to provide some other support, either pre or post-transplant, that would help us better prepare to follow them, and that would be helpful. And then the patient's role in AI-CDS should also be considered was another theme that was frequently brought up. So how you explain what you did to the actual person that matters the most, which is the patient, and how you came up with that decision, that's absolutely paramount. There's enough mistrust in medicine and in certain groups and even overall. So I think as transparent as you can be and being able to explain what you're doing is important. Another theme was needing to know who made the AI-CDS and their motivations. So who's making the tool or publishing the tool? What are their motivations? Is it a private company? Is it a consortium, a university? Who is developing the tool? If it's nonprofit or academic based or highly regulated like UNOS or OPTN, that would make it more trustworthy in my eyes. And again, this was one of our physician participants from one of the two centers. Another theme was desire to understand how the AI-CDS was developed. So this is getting at the transparency. So transparency is understanding the tool, understanding how the calculations occur and feeling comfortable with it. You don't necessarily have to understand every aspect of how the model works. You have to have a general, it cannot be explained that easily, but it's transparent to me because I think I get the gist of how it's developed. So this was interesting because this is sort of getting at the black box concept that is frequently talked about with AI-CDS, that it's too black box, it's impossible. There was this theme of, we understand we won't know every nuance of it, but as long as I can generally have an understanding. So again, coming back to those 6 themes that I just went over in the representative quotes, this was the conceptual model that hopefully can be a framework for developers and physicians and providers across the transplant teams that are being, shown AI clinical decision support tools and things to consider. So going back to our map, let's march on to the next step of AI applications, and that's for the waitlist. So in a study by Bert Simas and colleagues, they used the STAR dataset to create an optimal classification tree model, OCT, to predict candidates that had a 3-month waitlist mortality or removal from the waitlist. And then they used the liver simulation allocation model to compare their model, the outcomes with their model compared to the MELD score. So the optimal classification trees are a type of supervised learning with within the family of classification, or more specifically, these are non-probabilistic classifiers. So they are a type of decision tree algorithm. So I'm showing you this one because in Dr. Segev's lecture, he talked a little bit about decision tree algorithms. I think a lot of people have heard of them, but I'd like to take you a little bit step further to think about some of these other nuanced models. So Traditional decision trees use heuristic measures to decide how to split at each node, and they're generally understood to be what we call greedy because they make the local decision that's the most optimal choice for that node. On the other hand, these OCTs, they use mathematical optimizations to find the best split at each node while considering the global maximization of prediction accuracy. So they're trying to consider everything. And the benefits of that are the prediction is highly accurate, and they're also, because they're still in the decision tree category, very interpretable. So this, what you're looking at, is an example from that paper where they're showing just 2 of the splits for their study of MELD and bilirubin, each of the nodes. Obviously, they had other independent variables as well in their model, but this is just to get a sense for showing you how it's considering the whole tree. And then their model actually did show that it would reduce mortality on average when it was run through simulations by over 400 deaths per year, and improve survival was across demographics, diagnoses, and geographic regions. So the next step for another example is this decision point of accepting a donor. So clinically, we are becoming more and more comfortable with grafts that 10 years ago we probably would have discarded. One of these things that we think about is significant steatosis because it can lead to graft dysfunction and loss. So some researchers have been addressing the issue of middle-of-the-night assessments of donor steatosis with automated assessments of liver biopsy pictures. So you get your biopsy in the middle of the night instead of having to wait for the pathologist. We're using AI to interpret those slides. Now, Cesaretti's team had a novel approach aimed at using smartphone images. So not even of the biopsies, but actually what you see here, taking a picture of the liver itself. And then the liver part of that picture was extracted, and the image was broken down into these smaller test patches, and each patch was labeled either greater than or less than 30% steatosis. So then they use support vector machines to model and train their algorithm. So what are support vector machines? So let's talk a little bit about these too, because these are pretty common. You might have heard of them. So they are very powerful and they're very versatile. They're used in machine learning for both classification and regression, but you typically will hear about them more with classification. Support vector machines work by finding the 2 closest points of different classes and then drawing lines or support vectors from that point, from each of those 2 closest points to an optimal hyperplane that would maximize that margin between those points, which means, so then that gives you a way of separating those 2 categories of whatever it is that you're labeling. So they're good in high dimensional spaces. It's usually, this is thinking about it in 2D because that's what our brains can handle, but you can imagine it's doing this across high dimensional spaces. And it does a good job with having many, many variables, even if the number of dimensions exceeds the number of samples, which typically can be an issue with other machine learning models. They're memory efficient because they use just a subset of those the training points, which are those support vectors. So they find this information and then that's what they're using, as opposed to having to save all of the data and do things to it. They're also customizable because you can use different kernel functions like linear, polynomial, and sigmoid, and they can handle also non-linearly separated data. So you can imagine like drawing donuts around things if that's what needs to be done to separate things, but just doesn't always have to be a line. But the parameter tuning can be quite time consuming. So that's a positive and a negative sometimes. Their robustness means that they're less prone to overfitting than you might hear with other models. So they're pretty great. So in Cesaretti's study, they had, when they used these on those the hepatic steatosis pictures, they had a sensitivity of 97% and an accuracy of 89%. Okay, so to recap, we talked about evaluation and considers about equity. We talked about waitlist and optimization, or optimal classification trees, OCTs. We talked about accepting donors and SVMs. So now let's talk about transplant applications at the time of transplant. MRIs can be used for volumetrics and anatomic localization, but doing that, drawing those out and how it's been done in the past, is manually very time consuming. So Gross and colleagues aim to feed MRIs into convolutional neural networks, or CNNs, to automate liver segmentation, volumetrics, and radiomic feature extractions. So while their data set was used on HCC MRIs for segmentation on where to do segmentectomies, they do discuss that there's potential for obviously using this as risk assessment and planning for transplant in both the recipients and the donors. And you can see here that segmentation process happening. So convolutional neural networks. Let's learn a little bit more about these. And I know these come up a lot. They're kind of very mainstream right now with all the changes that are happening in AI. But hopefully I can break it down a little bit so you can have a better understanding on what's actually happening, at least a little bit more. So they are deep learning, and they're primarily used for processing data that's organized in these predetermined and regular formats, where the positioning of the elements within the area is significant for interpreting the data. So that's why you'll see them used with images, because the pixels and the colors are the dimensions that you have to think about. But they can also be used for time series data, because that's another example where the placement of the predetermined data, you can make sort of essentially picture matrices with it. So they utilize convolutional layers, pooling layers, and then fully connected layers to automatically and efficiently recognize patterns such as edges or lines across the images or textures on whatever data you're inputting into your model. So those three things. So convolutional layers, what does that mean? Convolutional layers are, imagine they're like the eyes that are scanning over that image that you're feeding in to find those patterns and complex features. And they do this by applying filters that slide, picture it like sliding across the image and creating new arrays or feature maps at each one of those. So you can kind of picture these are making these feature maps that highlight wherever some sort of interesting pattern is found, and then sort of stacking those. And then the second thing I mentioned was pooling layers. So pooling is like if you were to have a zoom out function where once you have those feature maps, you reduce the size of that feature map that was generated by the convolutional layer. And it does this by taking maximums or averages or some sort of way of just taking that one convolutional layer and simplifying it down. And that's what makes these networks so efficient. So the third thing I mentioned was these fully connected layers. And what they do is they take the identified info that you did with your eyes and the condensed info that you did in the pooling, and they are where decisions and patterns actually get made and simplified. And those are what develop into your output of the whole model. So I hope that makes sense and just gives you a little bit more language to understand when you're reading about these things. So Gross demonstrated excellent agreement, and data they were using was actually internal, external validation, and public data sets for volumetrics and radiomic features. So hopefully a lot of optimization and application of this in other ways during transplant. Next is the peri-transplant period. So this is going to be shortly after transplant. So after transplant, obviously graft failure and primary non-function is a major worry. So being able to predict these things would be for sure critical. And that's what Lau and colleagues were trying to do. So they took donor factors, transplant factors, and recipient factors to train a few machine learning models to predict death and retransplant within 30 days after transplant. And I mentioned they used a few models. So that's something that you will see in a lot of papers, is that people will say we're going to compare logistic regression to like 5 models. And that's a good thing because it's showing why are we even using AI, and if there's a benefit to even not needing logistic regression, which can be very interpretable. So they used a few different models. I'm going to focus in on the random forest model, so we can highlight that. So random forests are going to build on what we talked about earlier with decision trees. So you go from tree to the forest, and these are created by using an ensemble method and by taking different trees to multiple trees, not just your one decision tree, like I showed you with that the OCT, is they're going to take many trees and their predictive accuracy. And this is also going to be good for controlling for overfitting from just that one tree being too good and it's not actually able to be applied anywhere else. So each tree in the forest is trained on a random subset of the data and features. That's what you see here is the training data set gets fed in. You do a bunch of resampling and you create with one of the samples, one tree, and then you do resampling and you create a brand new sample and you create one of those trees with that sample. And then this goes on for many samples. And then each of those trees categorizes and comes up with an output, let's say yes or no, or whatever it is you're looking at. And so each of these trees would have a vote, is what we would say. And then those get pooled or combined, all of those votes, and that can be done through majority voting, or if these trees can also be used for regression and continuous outcomes. So it's either majority vote or averaging. So if you have all these trees and whatever had the most, let's say it was 100 trees, if 80 of them said yes, then the final combined voting would be a yes for the output of that data, the inputted data being fed in. So the accuracy and robustness using this method is improved as opposed to just taking the impact of just that single tree, because if just one of those trees had bias built into it, then that's all you know. But if you're doing this ensemble method across many, many trees, then you're able to sort of account for all of that. So Lau, using this method for where he was applying it post-transplant for graft failure and death and outcomes post-transplant, he determined that the random forests of the models that he tested had an area under the curve of 0.818. This is excellent. So what we just went through, we're going through this process. So we talked about the socio-technical systems and algorithmic fairness during this phase. We talked about the waitlist phase and mortality or dropout on the waitlist, and the model that you learned about was OCTs. We talked about accepting donors and donor organ quality using a method called SVMs, liver segmentation, and hopefully learning a little bit more about what we mean when we say convolutional neural networks, graft failure, and random forests. And then for this last step of long-term follow-up, that I'm going to refer you, Dr. Bhat will be giving a lecture or another webinar series, and she's going to be delving a lot more into that and all the amazing research that she's been doing. And so I did want to point out, though, that the referred step is an important step. I sort of started here because that's when they really walk into our doors and we're very involved. But this is an important part, too, that we should start thinking about. How can we build AI that will help to facilitate what's happening during the referral process and make it more equitable and get more patients that need transplant into our doors? So and I also wanted to acknowledge that there could be some pediatricians on the call or pediatric surgeons. So this is an example of more in their realm, and it can help us to start thinking about the selection bias that might be happening at time of referral. So Asher Bartlett and colleagues wanted to bring some objectivity to deciding who to refer for a transplant when kids present to the hospital with acute liver failure. And obviously, it's a devastating outcome to not transplant them. So a lot of people would go to transplant appropriately, but they were noticing that there are plenty of kids that, for whatever reason, don't get transplanted, and they actually end up doing really well. So they wanted to develop a model that can better stratify. So they created a novel, externally validated, predictive model of patient outcomes with pediatric ALF using common clinical variables that are on time of admission to the hospital. And they looked at how that could affect early referral to their transplant center. So they used lasso regression to narrow down to the important variables. So you might have heard of, it's lasso stands for least absolute shrinkage and selection operator regression. So it's a mouthful, so we call it lasso. And it helps you to use, it actually is using linear regression. And it shrinks the data. And essentially, the technique is useful for feature selection when you have tons of variables and you need to perform regularization and sort of understand what are the variables that we actually need to care about. You can use, obviously, expertise is what we mainly use for making those sorts of decisions, but this is helpful when you want to use machine learning to help with that. So they are what they then, so if you picture, they start out with a lot of variables. They use lasso to bring them down to the variables that they found important, and then they use something, a model that was using just logistic regression, which is very interpretable and easier for the physicians that are going to use the tool to understand. So that's what you see at the top here, the CHOP score. That's what you see is just the logistic regression part. And that they build a tool where then people can input those numbers. So they narrowed it down to just 3 variables from the many, many variables that they started with. And that helps people decide to refer or not to refer. So you might be wondering, I didn't talk about ChatGPT yet, so we can't have a discussion on AI without talking about ChatGPT. The potential for these large language models in healthcare is tremendous, and it's, like I said, evolving every day. So one example is text from imaging reports about HCC. And this is of particular interest because we all know that there's a lot of nuances in the reporting on HCC and the findings, and it's particularly important because we diagnose HCC largely just based off imaging. We're not getting biopsies as much. G and colleagues in this gastro publication, they showed how GPT-4 can help facilitate automated extraction of data about HCC from imaging, as opposed to manually having to extract it out. And whether that manual extraction represents us as clinicians going in and pulling it out, or as researchers having to go in and pull it out. So it's helpful across all, because if we're able to pull it out for clinicians as well, it can be shown in a better way within the electronic health record. So in this photo, you can see an example of the prompt for the study where they feed the data into a PHI compliant API. And this example doesn't have any PHI in it, but what they fed it into was at their university, they're able to feed the PHI information. So just picture tons of reports going in, and they give explicit instructions on the data to extract from those reports and how that output should look. So prompts are very important. There's a lot of thought that can go into how to build better prompts. And there are also instructions that they give it on the things that they don't want the model to do. And you can see on the right here, those were the features that they measured the accuracy on, and it was very accurate in being able to pull these out when compared to the manual chart review. So a little bit of background on GPT, since we're using it a lot these days. So they're from a large language model, which is a type of neural network that's been trained on vast amounts of data. So you've heard it's like the whole internet essentially gets thrown into it. And they're trained to understand and generate human language. So ChatGPT is powered by a type of AI called a transformer-based language model. And transformer architecture was a breakthrough in deep learning. And it wasn't that long ago. In 2017, this paper, Attention is All You Need by Vaswani. Transformers, what they do is they process all parts of the input data in parallel rather than sequentially. And they're utilizing a self-attention mechanism to understand the concepts and the context within the data. So the self-attention allows the model to weigh the importance of different words in a sentence or conversation when it's going to generate the response. And when generating the responses, the GPT is using decoding strategies that select the next word. And the techniques that it's using are sort of balancing out the trade-offs between randomness and determinism. So just randomly putting the next word in the sentence versus this is always going to be the next word in the sentence. It's balancing all of that, and it's enhancing the relevance and the coherence of the types of responses that you see. And so through this process, the GPT models, they learn language patterns, grammar, and a wide range of knowledge. And the big breakthrough was this concept of parallel work instead of sequentially only learning and only being able to see what just happened. So the future of AI in liver transplant is very broad. I'll give you some 3 just brief examples here. There's potential future for AI in the operating room. So we already have robot-assisted surgeries for a long time now. I think with the advent of those Apple Vision goggles, we can easily imagine, and the radiomics that I talked about earlier, you can imagine where there is potentially a way for seeing the imaging while you're actually looking at, it's kind of superimposed on your real world vision, things from the imaging. So you're looking at the liver, but you can see based off the imaging from prior to the procedure, what it looks like in the things you can't see under the surface. And then at the bottom here, you can see this is sort of like a holograph I'm depicting of an AI chatbot that's powered by a large language model, sort of like these virtual assistants that are just 24/7 support for patients, offering them advice, answering questions, reminding patients about medications and appointments. And you can see I'm sort of depicting that there's going to be these interactive technologies surrounding them in their everyday life. And it's famously said that we already have way more technology than we even realize. It's just not evenly distributed. So I realize that, not everyone is going to have this. And that's why I think it's important we think about how to implement all these equitably. And then last, the one on the right is just representing that I am imagining AI will be able to optimize transplant center workflows, reduce waiting times, improving patient care, and by efficiently managing the resources that we have, by being able to have almost this command center kind of picture that our coordinators are sort of just like easily able to understand everything that's going about the patients instead of all the information being buried. So the key takeaways for today was hopefully that the landscape of AI applications cover the entire process. The opportunities exist and are expanding with technology as technology expands, and then hopefully encouraging you guys to ask questions and be cautious and informed when developing these tools or thinking about implementing them into your practice. And as I said when I was starting, there's so much literature out there. I was cherry picking examples that would specifically touch on different AI applications and techniques, and I wanted you guys to be able to see it in different parts of the process. There's many other great examples out there, and if you want to learn more, I have here 2 review articles that I would encourage you to read. They're excellent, by Dr. Bhat and Dr. Span, and they will certainly catch you up to speed. And I'd like to thank everyone at Hopkins and my collaborators at NYU. A lot of the research that I presented today was supported by all the people on this slide, and they continue to support me, so I can't thank them enough. And I'm happy to answer any questions and have some discussion further about what's been done and what you all think can continue to be done. And you can feel free to contact me here.
Thank you so much, Dr. Strauss. That was really a wonderful presentation covering the breadth of applications in the liver transplant space. And I really liked how you brought in a discussion of the different tools and different applications. So really informing our audience about, the different methods that are available to them. So I think we'll start with a question here from Stefano Cesarin, and I'd actually encourage everyone on the call, to please feel free to post your questions in this Q&A. So Dr. Cesarin asks, how effectively predictive CNN, so convolutional neural networks, can be in terms of liver transplant outcome? Or are they only suitable to optimize diagnostic image analysis?
Yeah, it's a great question. I think it's evolving right now. So, which is sort of why I wanted to give you guys some background on what they're doing. So it's so important. And I guess I'm assuming you're some sort of clinician or provider, or maybe you're a developer. I'm not sure. But I think that this is where the rubber's really going to hit the road, is the more that we can educate ourselves as physicians to be able to just speak the language with engineers and data scientists and computer scientists that we're working with. So that way we can start to see how we can improve these models to work for what we need them to work for. So I was explaining that the convolutional neural networks are working. The important thing is that the space that the data is in is important. It's not just a list of variables and rows, but it actually matters the placement, and that's why time series analysis there's examples of using that, not in transplant, but where that can be something too, because you can imagine it's able to scan that kind of data as well. So my answer for your question would be that there's certainly other applications outside of imaging.
Great. Okay. We have another question from Omar Alomar. Thank you, Dr. Strauss. Great talk. Can you comment on the application of AI in machine perfusion and normothermic regional perfusion?
That's an interesting question. So I think that there's certainly going to be a space there. It's in terms of can you apply AI to this is always like a fun question for me, because AI has such a wide range in what it means, right? Like text prediction in your emails where it can see what word you want to say next is AI. It's AI if that lasso regression example that I gave, that wasn't the star of that paper. Like the star was being able to, what it came down to was being able to have that model at the end, but you used lasso to get a lot of data into something that us humans can manage. So as opposed to like the CNN examples do tend to be the stars of the show. They're doing a lot of great work, and that's sort of they're needed for that question and to be able to do that work. So it's hard for me to say. My answer would be yes, you can use AI in so many different ways that I'm sure there's an example for that application. Whether it's just a matter of what exactly you mean. Is it going to be in predicting the flow rates of the machines? You know what I mean? Because you can use data about the actual inner workings of the machines itself, or like taking a step back, is it about outcomes of people that use those machines? And time series data, for example, just going back to the kind of the last question with that. So there's so many different ways to think about it. I think we need to think more about where is it needed, where is it appropriate, who will use it, what is the clinical situation that it's improving. Like, so first, the big thing is just think about what is the clinical problem that you need help with. And then Dr. Bhat is just an amazing example of someone that's not just creating models, but actually implementing them, because she's doing a great job identifying like what is the clinical situation, pairing yourself with people that can help you. And then that's where the magic happens, and you're actually able to build things that will do something. So I encourage you, think about whatever your problem is and go find some data scientists and work through with them and see where it makes sense to apply it to that application.
Yeah, and I think, just expanding on that, I think there's so much data and longitudinal data that's generated during perfusion, right? And but the thing is, the data tends to be limited to a certain number of perfused organs, and ideally this sort of question, so predicting outcomes such as early graft dysfunction, would be the result of a multi-center effort as opposed to a single center effort, because AI really does work only when you have a lot of data and on multiple patients, multiple data points. So ideally, this would be the result of a multi-center effort. But it is a wonderful question, like, to work on, particularly given the amount of physiological data, clinical and laboratory data that is generated during perfusion. Let me see, are there any other questions from our audience? I mean, I'll ask you one in the meanwhile, Dr. Strauss. So what are your thoughts on ensuring equitable predictions? So I think, one particular concern that many people have, particularly in large data sets and registry studies, is the potential for bias to come into a data set. And so what are your thoughts on this, and how we can work as a community to ensure that we're working towards equitable outcomes for our patients?
Yeah, I mean, that's a great question. So I think that broadly, when thinking about equity and building these models,
Mm-hmm.
asking ourselves, why are we going to include race in the model? Does it make sense for what race even means? It's a social construct. Do we really think that there's a reason to include that in the model that is meaningful to whatever application it is that we're talking about right now, right?
Mm-hmm. Mm-hmm.
So I think that's just taking a step back to ask that main question, whether you're making a model or you're a clinician using a model.
Mm.
I would encourage everyone, I hope that's a big takeaway from today, is if someone puts something in front of you and you see that they included race in the model, please question it and say, is that something that I think that I want the score to be slightly higher and make them look higher risk, just because they got points added for being a certain race? And is that something I'm comfortable with for whatever application this is, right? We saw this in kidney, it's recently. So I think that's a big piece.
Mm.
So another piece would be, so let's say you're not including it, but you're still modeling something. You have to think about the data you're putting in and the biases that are potentially baked into that data.
Yeah.
Actually, I have another slide I'm going to jump to really quick. I love this quote that I read recently. This was sent to me by someone at AST while I was preparing for this talk. Shout out to Linda. So it was a great article. There's this series that they have done where they interview with people about AI. So
Uh-huh.
this blame the machine question. So if you're upset, this is a quote from the article, this down here. If you're upset about a machine learning model learning to kill more women than men, performing more poorly on women than men, but it learned from the data, maybe we should try to address the underlying problem, which is that more
Mm-hmm.
women die in this procedure, rather than saying, I'm so angry that the model has learned this thing. Let's use the fact that it learned to address the
Yeah.
let's use the fact that it learned it and use it to address the underlying issue. So that's where I think I challenge people to think about, how can we not just reactively make sure that these models aren't doing bad things, but use them to find where we're biased and get it
Mm-hmm.
at.
Mm-hmm. 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 Excellent. Yeah, I completely agree. So we have a question from Bima Hashtin, who says, thank you for the fascinating talk, Dr. Strauss. For all of the AI tools that are being deployed in the clinical setting, can you comment on best practices of how these models should be maintained to handle data drift or temporal shifts?
I love that question, because it's very important. And I think that especially after COVID just happened, right? So there's a lot of examples of models that were developed during COVID that were like, we should probably redo them all, right? Locally, and also what was happening in COVID at one place isn't transferable. But in terms of just like updating those models, they probably need an update. And this is a very important concept. The fact you even asked that question means you're at least thinking about it, which I think is the first best practice step, which is after you implement something, what measures are you putting into place to make sure it's being updated? And some of these principles can come from the quality improvement literature, just standards of practice and quality improvement. Whenever we talk about putting an intervention in place, or implementation science too, I should say. You put an intervention in place, you have to identify who are the key people that are going to maintain that intervention, and putting it from the beginning, saying these are our key performance indicators, or these are our key measures of if there's drift happening, and determining how often should we be recalibrating the model and rechecking what our accuracies and have changed, and the predictive accuracy of the models, how those have drifted. So I think people need to be monitoring it. It can't just run on its own. And I think the time and the things that you're going to be monitoring for should be from the outset, and that will be very helpful. But I would ask you, Dr. Bhat, I mean, you have put a lot of things in place, so maybe that's a teaser that you can talk about in your talk on what you guys do to maintain the work you've done.
Well, I think, the reality is that you can have a static model, but then over time, that model should continue to learn from the data, ideally. And you can even consider adding new variables to that model, including, say, the results of changes in therapeutic intervention, or any changes in the way someone was managed could be kind of fed back into the model in order to further refine it and train it. So I think the beauty of the AI methods that we work with is that there is that opportunity to be dynamic, to have dynamic modeling, as opposed to just relying on a set formula.
Right.
Yeah.
I want to say there was, I'll give another shout out to the AGA podcast, GI Bites. I am blanking on who did the talk, so I'm so sorry, but hopefully someone can tag them. But there was a talk on the vocal pen score, and they were it was one of the people that helped to create it, and they talked about this concept. So I would encourage you to find that podcast and hearing about their experience with it. It was a great discussion.
Actually, I have one final question for you. I guess we can conclude with this, because yeah. So what are your thoughts on working with, say, qualitative researchers? So bringing qualitative researchers into your work on AI. So say for the project that you published, what was your experience, and how would you recommend to our audience, working with qualitative researchers when they're working on AI projects?
Yeah, I mean, I think that qualitative, it sounds counterintuitive, because when you think AI, you think of, very hard science, computer scientists sitting around and thinking about numbers all day. And then you think about qualitative, and it's a much different mindset. You have to really kind of switch your brain. But they need to be paired. The research that we do in AI, it should be hand in hand with implementation science, hand in hand with human-centered design, which is inherently involving qualitative research. We need to be getting feedback before and after usability, whether it's human-centered design before you even make anything, to figure out what and where and who wants it. And after you made it, implementing it and getting usability testing and feedback from the users and the patients. I think all of that is critical. So I would say first point is just find your qualitative researchers, find people you love working with. I love the qualitative workers that I've gotten to work with. Dr. Sung is fantastic. She's taught so many people within our institution to train a little cohort of people that now are experts in qualitative research. So find your people, build relationships with them in the same way you would with your engineers, and learn to speak their language. I can't say it enough. I think being bilingual is, it's not just a world where we can just keep our heads down and do our doctor clinical thing, and not expect that we need to learn how to interact with others if we want to change things. So I think being respectful and just working with them and learning the lingo, learning how, and being open-minded, because it can be very different than what language that we use in the clinical mindset, and like opening up and making mind maps. When you sit down with your first qualitative person, they want you to mind map about your thoughts on a problem, or they want you to memo. Like memoing and mind map are serious techniques used in qualitative research that I would say, as a researcher who's new to it, be open to these things, jump in, learn new skills, and work with them, because it's only going to make your projects better.
Excellent. So I think on that note, we will conclude this wonderful webinar. Thank you so much, Dr. Strauss, for sharing your experience and your knowledge on AI and liver transplantation. And I'd like to hand this over to Brian Valeria from the AST to conclude our webinar for today. We hope that you'll be able to join us at the next webinar on AI and liver transplantation in about a month or so from now. Thank you.
Thank you so much. AST would like to thank Dr. Strauss and Bhat, the leadership of LICOP, TxAQM COP, and TCC COP, and all of our attendees for today's session. Please look for an email from Zoom in about a week directing you to a copy of the recording available free and on demand. Finally, please remember to complete the evaluation survey in Zoom and visit myast.org/education to learn more about and register for our upcoming webinars. Thank you all again for today's wonderful session.